Hi, good evening, all.
Good evening, ma'am.
Yeah, good evening.
Good evening,
Yes, so today we are going to see some basic distributions from week 0.
ma'am.
Can you
Can we
also
ask doubts here, like some activities and some lectures?
You can ask me doubts once I explain the distribution, then you can ask. Okay.
ma'am, after the distribution, can you give us a brief about conditional probability, like marginal conditional probability?
Okay, fine.
Thank you.
Yeah. Okay, so the first basic distribution that so in your stats 1 course, you must have seen the Bernoulli and the binomial distribution. So the Bernoulli distribution is the most basic distribution that we have seen before. So what happens in a Bernoulli distribution is like you have an experiment, you perform an experiment, and any event you define is either a success, like occurrence of an event, you define it as a success, or and the non-occurrence of that particular event, you define it as a failure, right? So if let's say you have a probability space of probability space where S is your sample space, E denotes your collection of all the events, and P is your probability of success, right? So if you take any event A from your set of events, and you say the probability of that event is given by small p. So I am denoting this event A. I'm saying this event A is a success. Okay, so the occurrence of the event A is going to be your success, and the non-occurrence of the event A is going to be your failure. So if the probability of success is given by P, then what is the probability of failure going to be?
1 minus B.
1 minus P.
1 minus B, right? So there are two different terms. One is single Bernoulli trial and other is repeated Bernoulli trials. So what happens in single Bernoulli trial is like you have a sample space and you just have one trial, like you perform an experiment just once, and that is a trial. Like suppose you toss a coin. So this is just one trial. You tossed a coin, you tossed a coin one times. So you have two outcomes here. One is success, another is failure. So let's say if I say my success is getting a head, so my failure is going to be getting a tail. So usually we denote the success by 1 and the failure by 0. So our sample space in that case, so if you have a single Bernoulli trial, our sample space is this S here is for success and F here is for failure. So we denote as success as 1 and failure as 0. So sample space becomes just 1 and 0, where 1 is the probability of occurrence of an event and F is probability of non-occurrence of an event. So such kind of situation, we call it as a such kind of distribution, we call it as a Bernoulli distribution, and it is just one trial. Now, if we have like if we perform the same Bernoulli trial, suppose let's say n times. So and each of the trials are independent. So in that case, like if in one trial you have just two outcomes, that is 0, 1. So if you perform the experiment n times. So how many outcomes are you going to get?
To the power n.
2 to the power n times, right? So this is basically what you call as a repeated Bernoulli trials. Like you have a Bernoulli trial, you perform the same trial again and again, and the probability of occurrence of each of the trials are going to be independent of each other, and your success, like if your success is going to be the same and the probability of that success is going to be same throughout the trials, then in that case we say that that kind of distribution that it models is binomial random variable. So what happens in binomial random variable is it basically models the number of success that you get in n repeated independent Bernoulli trials. So let's say this is my first trial, second trial, third trial. I perform the experiment n times. So if I perform my experiment n times, so how many successes I can get? Sorry?
N times.
N times. Okay. Can I get 0 success?
Yes, also 0
Yes,
to n.
ma'am.
Yes. So
Zero.
if I have performed an experiment n times, so number of successes can be either 0 or 1 or 2. It can go till n. It cannot be more than n, right? So such kind of situation models the binomial distribution. So let's say a few examples. So if I have a single Bernoulli trial, let's say a fair coin is tossed once. So what all the outcomes we are going to get? We will have a
1
head.
to the power 2.
It is just one head and tail, right?
Yes, ma'am.
Outcomes is just going to be head and tail. And if I say success is getting a head, failure is going to be getting a tail. So if I denote my success as 1 and failure as 0, so what is probability of success?
1 by 2.
1 by 2. And probability of failure?
1 by 2.
1 by 2.
1 by 2, right? Now, if I say a fair die is thrown, and what is the probability of getting a number less than 3? So if you throw a fair die, what all outcomes you are going to get? It
1,
is
2, 3, 4,
1,
5,
2, 3 up to 6, right? Now, what is a success?
2 by 6.
No, like how do you define
1,
the
2,
success?
1 by 2.
Probability of getting a number less than 3. So success is getting a number 1 and 2.
2.
And failure is going to be like
3, 4,
3
5,
to
6.
6.
3, 4, 5, 6. So all this is easy, right? If a single, like if an experiment is performed once, you can identify what is success, outcomes, and failure, etc. So if I say, okay, here it says a fair coin is tossed 2 times. Find the probability of probability that 2 tails are there. What is the probability of occurrence of 2 tails?
1 by 4.
Okay. Okay, so these are all very direct, right? You can easily find it. So what is the probability of occurrence of at least one head?
1 by 4. 1 by 4.
3 by 4.
3 by 4.
3 by
3 by
3 by
3 by
4.
4. Right?
3 by 4.
Yeah. So how did you find it? So we had to find at least one head. So outcomes, if we know that if you toss a fair coin 2 times, your outcomes are going to be head tail, tail head, and tail tail. And if I want at least one head, so these three like our event A is going to be HH, HT, and TH, and the probability of this is going to be 3 by 4, and failure is 1 by 4. So these are very basic distributions. These must you have seen in Starts 1 course also. So I assume that binomial and Bernoulli is quite easy. Yeah, if you have doubt from binomial or Bernoulli, you can ask me.
Basically, what I understood is
Mhm.
is discrete type and it has a success and failure, for example.
Yeah.
When we repeat the number of trials, then we can convert it into binomial distribution.
Your voice is not very clear. Can you repeat again?
In case of a Bernoulli, it
Huh?
is a discrete type of distribution, and in which it has a two types, either yes or no, or success or failure, like that.
Right.
And when we do the number of trials more than once or twice, then it is converted into binomial distribution.
Okay, so you're asking if it is just one trial, we are saying it is Bernoulli, and if it is more than one trial, we are saying it is binomial. Is it your doubt?
Yes.
Okay, so what Bernoulli distribution is something where you just have like you have just performed one trial and you have defined some occurrence of some event as success and occurrence of another event as failure. So what happens in binomial distribution is, so it is the repetition of n Bernoulli trial. Like you perform like the first trial is again Bernoulli P, second trial is against Bernoulli P, and each of the trials that you have performed are independent. Each of the trials should be independent. So basically it models like how many successes that you can get in those n repeated Bernoulli trials. Like if I say I have tossed my coin 3 times, so if I'm interested in like number of heads should be greater than 2, right? So something like that. So in each of the trial, like if I toss my coin first time, it is going to be just HT, right? It can be either H, it can be either T. Again, the second trial, it can be H or T. Third trial, it can be H or T. And in such way, you will have 8 possible cases.
Okay, understood, ma'am. Thank you.
Okay, so if you have a binomial distribution, its PMF is given by n choose k, p to the power k, 1 minus p to the power n minus k, right? Where n is like how many times the trial is performed, and k is number of successes that you get in those n trials, and p is probability of success. So
Can we, ma'am, do
So,
this?
ma'am, in binomial distribution, these 3 parameters came. N is the
no,
NPK.
in binomial you have just 2 parameters. So in case of Bernoulli, you just have one parameter, that is p, and it is called probability of success.
Success.
In binomial distribution, you have 2 parameters. One is n and other is p, where n is number of trials, but not number of Bernoulli trials, and p is probability of success.
Okay. And this K is given in the question.
K, okay, yeah, like K is number of successes. K is basically number of successes.
Excuse me, ma'am. Just to reiterate for my clarity, can I repeat something of what you said and get clarified?
Yes, sure.
So basically, when you say Bernoulli, there is only a possibility of success or a failure. Like if I say I throw a dice and say if it is even, it is a success. If it is odd, it is a failure. Though there are 6 numbers, it is still a Bernoulli.
It is Bernoulli, right?
Okay. And the probability can be anything, is it?
Probability can be anything. Like just the example you took, you said I throw a die once. So you have 1, 2, 3, 4, 5, 6.
Correct.
Right. So if I'm saying my success is getting an even number, so this will be like contain 2, 4, 6, right?
Okay.
This is my success.
Okay.
So my failure is going to be like A complement is going to be 1, 3, 5. So what is the probability of success?
Okay. It's only about success or failure, but
it's
not
it's only about success. Yeah. It's only about success and failure.
Okay. It is not about what entails the success or failure. Like here, if it is 2, 4, or 5, it can be anything.
Yeah, it can be anything. Depends on how do you want to define your success to be.
Okay. On an extension of this, can I ask, is there something called a Bernoulli distribution, like there's a binomial distribution?
Yeah, such kind of distributions is called the Bernoulli distribution.
Okay.
I mean, whenever you have just like here, you just had you have just throw a dice once, right?
Correct.
and you have defined your success, you have defined your failure. So this we can say that this is a Bernoulli distribution. This model is a Bernoulli distribution. The probability of success 3 by 6, like 1 upon 2 here.
And can we solve that above question by using this binomial distribution?
Which question? Wait.
This one?
Question number A15.
This one, ma'am. Probability of getting at least one head.
Okay, probability of getting at least one head. So if you toss a coin 2 times, right? So your outcomes are going to be HH, HT, TH, and TT. Right? So I'm interested in probability of probability that there is at least one head. So number of head that I can have. So let's say your X number of heads that I can have is either 0 or 1 or 2. We cannot have more than 2. So what is the probability that you have at least one head? It means probability that X equal 1 plus probability that X equals 2, right?
Yes, ma'am.
Because we're asking about exactly at least one head. So
Greater
what
than
is,
equal to 1.
yeah. So what is the probability X equal 1?
2 by 4.
2 by 4.
So if you want to go by this
Ma'am,
binomial
we can-
distribution,
Binomial distribution.
We can also find out by
You see- you
finding
see-
out the probability of X is
Huh?
equal to 0. 1 minus probability of X is equal to
yes,
0.
1 minus probability X equal to 0. Yeah, that is much easier. Yeah, correct.
And what is
Ma'am, I
this?
have a question.
And by
Uh,
binomial distribution, you are
Yes, so
you are
okay, let me
what is-
finish this first. So if we want to do this using the binomial distribution, so what is happening here is like you can either find this probability or you can find 1 minus probability X equal 0. Both will give the same answer, right? Because you have the range of values that X is taking is just 0, 1 and 2. So this is same as probability of like 1 minus probability X equals 0. So let's say I want to find using this probability X equal 1 plus probability X equal 2. So what is the probability that X equal 1? It means that out of 2 trials, you have like one head, right? So 2 C1,
1.5 power 3, 1.5 power 2.
right? And what is the probability that X equal to? It is 2 choose 2. 1 by 2 to the power 2. So this is 2 by 4 plus 1 by 4, that is 3 by 4. Right?
okay, ma'am. Thank you.
Ma'am, X is just like K.
Yeah, sorry. Repeat, please.
Ma'am, X जैसे K है वैसे X है यहाँ पे.
Yeah. Yes. So this K here is 1 and 2.
Ma'am, what was the remaining part? 1 minus p to the power n minus
Okay.
k.
So what
What?
it is like finding X equal 1 plus probability X equal to 2 is same as finding 1 minus probability X equal 0. Do you agree with this? That both are going to give the
Yes,
same
ma'am.
answer.
Yes, ma'am.
Right?
Yes, ma'am.
Yeah. So basically, this is an easier method. Like you just have to find probability X equal to 0 and just subtract from 1.
Ma'am, in formula we also have no 1 minus p to the power n minus k. There is that component.
1 minus, sorry, can you repeat?
1 minus p to the
Huh?
power n minus k. In Bernoulli distribution, we also write no, that.
Yes.
choose-
So
so-
this is exactly what it is. No, I mean, n choose 1. So 2 choose 1. P to the power k. So p is 1 upon 2. P is 1 upon 2 to the power 1. And what is 1 minus p? It is again 1 upon 2. And 2 minus 1 is again 1. So it is going to be 1 by 2 whole square. Similarly here, 2 choose 2, 1 by 2 to the power 2 and 1 by 2 to the power 0, right? So this term is there. It just 1 minus p is again 1 upon 2 in this case.
Yeah, merged it.
I mean, this question we will take n equals to 2 or n equals to 4.
And it will be 4.
N equals to 2.
Okay,
Two,
so
two.
why it okay, if you have asked this, like why your n should be 4?
I think number of the outcome
Number
is
of
4.
outcomes are
No,
4.
n is not number of outcomes. N is number of trials. N is
Okay,
number
okay.
of Bernoulli trials. So here you are performing the experiment twice.
And the random variable takes the value from 0 to n.
0 to n. So
Yes.
it is 0, 1, 2, right? So x here is a binomial distribution with n equal to and p equal 1 by 2. Right?
Yes, ma'am. Thank you.
Ma'am, K here
Yeah.
will be 2.
Sorry.
K.
So k is varying from 0, 1, 2. Either you can have 0 success or 1 success or 2 success. So how is a success defined? Success is defined as getting ahead. Getting at least 1 head.
Okay.
Here,
No, sorry, getting ahead. Sorry. Yeah, what?
Is the random variable?
So what is random variable? I have defined my random variable x to be getting ahead.
Okay.
Number of heads in like 2 tosses of a coin. This is my random variable.
Okay, ma'am. Please go ahead, ma'am.
Okay, yeah. So after this Bernoulli and binomial, you have something called the geometric distribution. So
If I may interrupt just one second.
Yeah,
I have
please.
one question. You have mentioned in the binomial distribution that the sample space for n trials would be 0, 1, 2, and up to n.
Yes, right.
So could we also call this the range?
Yes, this is the range of the random variable. So if I'm saying
So range and sample space is one and the same thing?
Yes.
Okay, thank you.
Yeah.
Range could be different and sample space is the total, I mean,
Correct.
what are the outcomes
So-
you can take.
Possible
Range could be different. How come
No,
range and sample space are different?
sample spaces like all those outcomes that
All
you
the
get.
favorable
All the
outcomes.
favorable outcomes,
Favorable
right?
outcomes.
That is a
Then-
sample space.
And
So
range is
range is like what all values your
Possible-
random variable that takes, what all possible values your random variable can take.
so both can be different, right?
So in this case, like I have modeled a binomial distribution. So it basically gives it models the number of successes. So depending on what is my success, right? So I have just given a value associated to it, like number of successes can be 0, 1, 2, and so on. So in place of, let's say, if I have the same, if you look at the same example.
Range can be a subset of sample space.
So if you look at the same example of 2 toss of a coin, I will say my sample space is HH, HT, TH, and TT. Right? And if I have defined my success to be getting ahead, getting number of head, right? So number of head can be either 0 or 1 or 2.
So this is the range, I think.
This is the range, and this is what the sample space is basically.
But that's when range has to be derived from your sample space, right?
Yes.
But both can't be similar, as sample space contains all the outcomes
like
which don't have head.
Yeah, so it basically gives the values that are associated with the
Because in sample
outcomes.
space you cannot assign any value, but in range you assign a value.
No, like if you have a sample space, you have defined some event, and on the basis of that, you are writing your range.
Yes, you cannot assign value in a sample space like HH, HT, but to in a range you are assigning a value like success value.
Yeah, I get that. Yeah, right. Yeah.
Ma'am, can you explain the difference between range and sample space once more?
Yeah, so see, if I have the same example, if you have tossed your coin 2 times, so these are the outcomes that you're going to get, right? HH, HT, TH, and TT. This is a sample space. Now, on the basis of how I define my success to be, so I have defined my event to be like number of heads, right? So number of heads can be either 0 or 1 or 2. So this is my range of value that is going to take. So it all depends on how you have defined your event to be.
Okay, ma'am, got it.
Yeah. Okay. So moving to the geometric distribution. So, okay. So binomial distribution models the number of successes that you get in the n independent Bernoulli trials. So what happens in geometric distribution is like it models the number of trials that is needed to get the first success. Okay. So the examples that we can take is like number of trials that is needed to get the first head. So the first head you can get in like the first trial or the second trial or the third trial or the fourth trial, and it can go on, right? Similarly, if I throw a die, so if I define my success to be getting an even number, so I can get an even number on the first trial or on the second trial or on the third trial, and so on. So basically, such kind of situation models the geometric distribution. So what are the range of values that it can take?
1 to n.
Okay. Why 1 to n?
Could you repeat once again?
Sorry, infinity.
Can
Yeah,
you repeat?
Yeah. So what happens is like in case of geometric distribution, it models the number of trials that is needed to get the first success. Like for example, number of trials needed to get the first head. Needed to get the first head. Second example I can take, number of trials needed to get an even number when you toss a coin, when you throw a die. So if you look at such situations, so how many trials that is needed to get the first head? Can you mute yourself?
0 to n. The range would be 0 to n, right?
N trial, ma'am.
Yeah. So not n, 1 to infinity, right?
1 to infinity.
Yes, ma'am. 1 to infinity.
1 to infinity. So either I can get my first, like I toss a coin. It is not necessary that I get my first head on the first trial, right?
Sorry,
right?
ma'am. Sorry to interrupt. Can you just repeat this part again, ma'am, please?
Yeah. So can you mute yourself? There is some noise. Who is there? Okay.
Rishabh Kumar Singh.
Yeah, I muted. Okay, fine.
Thank you.
Yeah. So what is the geometric distribution? Where does the geometric distribution occurs is like whenever you have a situation like a number of trials that you need to get the first success. So in such kind of situation, we call it as a geometric distribution. So for example, like you have a coin, you have a fair coin, and you're just tossing the coin until you get the first head. So if so how will you define your success in this case? How will you define the success?
Ma'am, getting first head.
Getting the first head.
Yes, getting an head, right?
It could either be getting first
Getting a first head,
not
No,
first
not
head,
first
just
head.
getting a head. Getting a head is a success, right?
Because we will stop when we get a single head.
Yeah. So getting a head is
if we are we are getting a single head. Okay.
So you have a coin, you are tossing it repeatedly, and you will stop unless you get the first head. So I have defined my success to be getting a head. So either you can get your head on the first trial, or you can get your head on the second trial, or you can get your head on the third trial, and so on, right? So either it can be on the first trial of first position or second or third, and it can go on till infinity, right?
Yeah.
Yes, ma'am.
This is clear?
Till we get
Like there is no limit, ma'am.
Yeah, there is no limit. Like it is possible
Until-
that you may not get tail for a head for a long
Yes,
number
ma'am.
of
It
trials.
happened with me.
That means we
Okay.
stop when we get first head.
Yeah.
That
The
would be infinity.
game got over and I didn't get a single six.
Okay. So similarly, you have some. I have taken another example. So it says like you have a fair die, and you are going to throw it unless you get an even number. Okay. So what is a success here?
Getting an even.
Getting an even number is a success, right?
Yes.
So success is getting an even number. So what is the probability of success here?
3/6, 1/2.
1/2.
Two.
So how do we write this as? We will write this as geometric 1/2. Okay. So it is represented as geometric 1/2, where 1/2 is a probability of success. Fine. So how do you give the PMF of this distribution? Okay, so let's say you can get the first success on the first trial or the second trial or the third trial and so on. So what is the probability that you will get the first success on kth trial?
Okay. Probability of
1 minus 1 minus
1 minus p
p to the power k.
K
1 minus p to the power k minus 1
and minus 1. Not there, ma'am. Minus 1. I think
into p. Yeah. So if Turtle.
Oh, no, it's okay.
Ma'am, what is this? This is a PMF of this.
This is the PMF
Geometric.
of geometric p distribution.
Okay.
Okay. So what does it mean? It means that you are getting your first success on the kth trial, right? So if you are getting your first success on the kth trial, so you have 1, 2, 3. Let's say this is your kth trial. Okay. So if you are getting first success on the kth trial, it means on the first k minus 1 trial, you have all the failures. And what is the probability of failure? It is 1 minus p. So 1 minus p into 1 minus p, like you will multiply it to k minus 1 time. So 1 minus p to the power k minus 1, and on the k trial, you have a success. So into probability of success, right? So is this formula clear? Like how did it come?
Yes, ma'am.
Nikita, I have one doubt
Yeah.
here related to
Please.
geometric distribution.
Yeah.
Can we derive it from the Bernoulli binomial? Because this is the first success in repeated independent Bernoulli trials, right? Geometric distribution.
Yeah, first success in repeated and Bernoulli trials. Right.
So can we try to derive it from the Bernoulli, because I'm not getting binomial?
This is not
with the
binomial.
PMF function, binomial function. PMF is then NC.
Why do you want to derive it from binomial?
Because it's also defined as number of trials for first success in repeated independent Bernoulli trials.
You have to consider that first k minus 1 trial is a fixed. Okay. Then after that it comes to your success.
Okay.
So you have
wait. So what you can say is like binomial distribution and this geometric distribution model is a different thing, right? Binomial
But
says
the same definition.
Binomial says number of successes in n repeated independent Bernoulli trials, right?
Yes,
Number of successes. And what does geometric distribution models? It models like the number of trials that you need to get the first success. Fine.
Actually, I read this in the PPTs or somewhere. The first success in repeated independent Bernoulli trials, binomial trials, Bernoulli. Yes.
Bernoulli trial, not binomial, but Bernoulli trials. So this is how we have derived. See, so you have, let's say I have, I am repeating
geometry,
my,
in geometry distribution, we are finding the number of trials.
Yeah, number of trials that
number of possible trials.
But these trials are
probability.
Anything which has only 2 outcomes can
I think these trials are similar like binomial, right?
No, this is
Bernoulli trial.
Only 2
You have a
possibilities
Bernoulli
are there,
trial.
either success or failure.
Here you know that first k-1 trial is a failure. Okay. So so that's why k-1 is it's a kind of a, if you can consider the k-1 is a failure. So
yes,
obviously,
here also we have only 2 cases, success and failure. And
See,
these trials
I
also
will
similar
explain it
to
again.
Yeah, please.
Yeah,
But listen one thing.
Yeah, okay.
These trials are similar to binomial, right? Because
no, trials are Bernoulli trials.
No,
You're talking
no,
about Bernoulli trials.
no, actually here in binomial, we are conducting the trials complete. If n number of trials possible, I am conducting all n number of trials and I am counting number of success I got. That is binomial. In geometry, what we are doing, I am conducting trials and I am stopping my trial when I get the first success.
Yes, here I am thinking as n is my in binomial n comma p, right? So here n as my trials in geometry and p as my probability. So it will become my first success in binomial, right?
Madam, you don't know the n.
But you don't know the n. That's what. So in geometric, what is happening is like you don't know what is your n, right?
Yes.
You just know you have a Bernoulli trial and you're repeating it unless you get your first success. Like what I said here is like you had a coin and you're tossing it repeatedly unless you get the first head, right? So getting a head was a success. You had a Bernoulli P trial, like your success was getting a head.
Yes, after getting the answer, I cross-checked whether these two are matching, but the answers
what these two? What these two?
This NC1, right? In n trials, the first success in binomial. Because n we are getting from the geometric distribution as an answer, we will get right. We will confirm what is n.
There is no n here. I mean, the number of trial is not fixed in geometric distribution. That's what
binomial it is. In binomial it is.
Yeah, in binomial we are performing the like repeatedly Bernoulli trial n number of times. But in geometric, we are not doing it. We are just saying like on what trial you're getting the first success. We don't know on what trial you're going to get the first success. It can be either on the first trial or on the second trial or third trial, or it can go till infinity. So we don't know what my actual n is. I am just saying, let's say, I am getting my first success on the kth trial, right? So what is the probability of getting my first success on the kth trial? So if this is my first trial, this is my second trial, third trial, let's say this is my kth trial. So what is the probability that I get my first success on this kth trial? Okay, it means the first k-1 trial, it is all failure. First trial is failure, second trial is failure, third is failure. So k-1 trial is also failure. So we are just multiplying all these probabilities because all the trials are independent. So what is the probability of a failure? Probability of failure is given by 1 minus p. Right? And again, it is 1 minus p. And you will multiply it for k-1 term. So it's just 1 minus p to the power k-1 into p, because you have the success on the kth trial. So this is how we have derived this probability distribution.
Geometric.
Okay, Nikita, I will ask my doubt while solving the problem.
But it's a, if you see it in a bigger way, it's a kind of a Bernoulli only. The failure.
Yeah, it is. Each of the trial is a Bernoulli trial. Each of the trial is a Bernoulli trial.
Sandhya, do you remember we had a question in stats 1 about which, you have this guard has a bundle of, I think, 20 keys and he's trying on the door. So at say trial number, say which number trial that he will get success. So if say what is the probability he'll get it on the say 6th key. So you will assume that on the first 5 keys he'll have failure. So what is the probability of failure? 1 minus p.
Yeah,
What is the probability of
yeah.
success?
Yeah.
So it's something like that one. If you remember, we did such a question.
Yes, sir. Yes, Divya.
Ma'am, that was the question of the probability mass function where we can add all those things to one and we can get that thing, if I'm not wrong.
I don't know which problem you're talking about. It was in stats 1,
It's
right?
okay, Nikita. Let's move on. I will ask my doubt when the opportunity comes.
Sir,
Okay, let's take this.
Ma'am, just a quick clarification. Ma'am,
there was a question in lecture.
There's okay.
Just a second.
Toss a coin 5 times.
Okay.
Toss a fair coin 5 times. Head is 0, tails is 1. Sample space has 32 outcomes.
Yes.
This question was on Bernoulli trials lecture.
Okay.
I had sir has solved this using Bernoulli trials. I had done solved.
Yeah, so this is
geometric.
5. This is repeated Bernoulli trial. No? Like you are performing your experiment like 5 times. Like
yes, ma'am.
So it is repeated Bernoulli trial.
Yes, ma'am. Same thing I want to say that I had solved this question using geometric distribution.
Which
but the answers are same. This question, sir has solved using Bernoulli trial, and I had solved using this formula.
Yeah, it's the same thing.
Yes, ma'am.
Yeah.
Ma'am, just a quick clarification, ma'am.
Okay.
Yeah, like in geometric distribution, we are saying that it can go up to infinity, right?
Right.
So are we saying that geometric distribution we study only for infinite number of experiments? Can we perform this experiments where we have counted number of experiments? Just to give an example, take the example of 2020. There are 120 balls, right? In 20 overs, there are 120 balls. So wicket or no wicket, wicket or no wicket. So it is by success and failure, right?
Okay.
So can't I carry out this experiment for 120 balls? That what is the probability of getting?
Okay, so here it is like like number of balls is fixed.
Correct. That's my question. Yes.
So the way you will define your geometric distribution is number of balls that you need to get the first
correct. Yes.
Whatever it is.
Wicket.
That is how you will define the geometric random.
My question is that geometric distribution can be applied where number of experiments are fixed also, right? That's my point. Can we apply or not?
Number of experiments are fixed, you're saying?
Yes, yeah, I have 120 balls. It means I can perform only 120 experiments, right? And if I ask a question that what is the probability of getting a wicket on 60th ball?
What is the probability of
getting the wicket on 60th ball, right?
First success on 60th ball. Yeah,
correct.
That is fine.
So it means
like you're getting the first success on 60th ball.
Correct.
So this models your geometric random variables.
But here the NCK will vary. NCK additional will come. Binomial.
Ma'am, NCK will not come into picture.
No, it is right.
Because I am getting my first success on 60th ball. It means till 59th ball I am getting failure.
Getting a failure, right?
So it means 1 minus p to the power 59 into p. Whatever is my probability, right, ma'am?
But when we take 120 as binomial, the answer will vary, right?
Correct. When I'm going for binomial distribution, ma'am, when I'm going for binomial distribution, then answer will vary. You are right, ma'am.
That's what my actual doubt is. I was unable to explain. That's my actual doubt.
Okay, so you are saying like if your n is 120, what is the probability of getting first head, like one head?
No, wicket.
Right? Wicket is a success. Okay. Probability of getting one wicket.
Yes,
the probability of getting wicket in each ball is same or not? That is a very important thing.
Yeah. So okay, let me write. So
let us assume it's same.
So probability of getting like one
just
wicket.
First success in 60th
one wicket.
ball.
Just wait. So probability of getting one wicket in 120 balls, right? So how is it same as probability of getting first wicket in 60th ball? Both are different, right?
Yes.
Here you are saying here what you are finding is like in 120 ball you want just one success, right? And here you are saying is on the 60th ball you want the first success. Both are not the same thing.
So the first one is binomial, right, ma'am? The
first one is binomial, second one is
geometric
random variable.
Yes. Yes.
No, ma'am. How first one is a binomial?
So
we are talking about only one success in 120 balls.
Yeah,
appear on any ball, and it can appear on any ball.
Maybe
yes, you can get.
Yeah,
answer will vary because both are different situations. In the first case, you are saying
answer will not match
because the situations are different. In the first case, you are interested in finding the probability that in 120 ball you should have just one wicket. So that one wicket can occur in any of the 1 to 120
balls,
right? But the second situation is different.
I'm talking about getting a success on 60th.
So, ma'am, can we define the second situation as different from the first situation? That in the second situation, we are sure that the previous 51 cases or experiments are all failures.
Correct.
59.
Okay.
Yeah.
To avoid confusion, just let's write 60 here and 60 here. Okay, we just have 60 ball, and saying that you are getting one wicket, probability of like one wicket in 60 ball. So
and
that
it can be
one
any ball. It can be any.
It can be any ball. So
but in the second case, all the 59 previous ones are failures.
Are failure. 60th is
okay. So that makes the difference, right?
Yeah.
And that makes second one as a geometric progression.
Yes. And also the probability of success, probability of success here is getting a wicket should be same throughout the balls, right? That also matters here.
Right.
Ma'am, in first case n is 60 and in second case n is 120, right?
No, I mean, let's say it is 60, overall 60. You have 60 balls and the first case you are finding like what is the probability that just one wicket will be taken in 60 ball. Second, you are finding what is the probability that the first wicket will be taken in on the 60th ball. Okay, so there's a difference there. So the probabilities will not be same, it will vary.
Ma'am, just a follow-up question.
Yeah.
Might be a premature question. Like here, whatever probability we are assigning here, this is called prior probability, right?
Sorry, what probability?
Whatever probability we are defining here, like 1 minus p and then p, right? So this is called prior probability. Like already in question, it is being given, right? In question, generally it is being given, right?
What probability of success you mean?
Probability of success, right? It is being given.
Yeah, it will be given. Yeah, it will be given.
But in real life, when we are modeling the real situation and real life situation, then how to get this prior probability?
Yeah, so there you will have.
It might be a premature question. We can park it to discuss some other time. But this is just a doubt. Okay, the probability of success in question is generally being given, right? But
yeah, it will be given. But in real life, you will have to figure out some ways to find it.
Okay.
Yeah. So this was all about the geometric distribution.
No, in real life, do we really like carry on an experiment for infinite times? We don't.
No,
right?
it is not infinite
not
times.
feasible.
Of course, it is not possible.
No,
Yeah.
When you say, for example, when you are dealing with the stock market, right? You are trying to project stock price. Then of course you are supposed to consider something. No? That's a real life situation.
Yeah, right.
Ma'am, please continue.
Yeah, okay. So continuing with geometric distribution, you have something as negative binomial distribution. So what happens in negative binomial distribution is like your So geometric distribution models the like number of trials that you needed to get the first success. So similarly, in negative binomial, what happens is it models the number of trials needed to get R successes on the kth trial.
So, ma'am, now what we are talking about?
I'm talking about negative binomial distribution.
Okay.
Negative binomial. So what happens here is like number of trials needed to get R successes on the kth trial. So whatever success is whatever success you define it to be. So in geometric distribution, we were interested in finding the probabilities where the first success occurs, right? Number of trials on which the first success occurred. But in this case, what we are saying is number of trials that you need to get R successes. So let's say on the kth trial, if it is the kth trial, on the kth trial you have Rth success. On the kth trial you have the Rth success. So it means the remaining first k minus 1 trial, you should have R minus 1 successes, right?
Yes.
Yes, ma'am.
So if a situation like this happens, so how can you write the distribution function of negative binomial? Any guesses? How will you write the distribution function of negative binomial?
It's a k minus
1,
K
R
minus
minus 1,
C R minus 1.
1 minus P to the power K minus R into P to the
Okay,
power.
one by one. Can you repeat again, Aditya?
Yes, ma'am. Ma'am, K minus 1, P R minus 1.
Okay.
Into.
Okay.
1 minus P.
Okay.
To the power K minus R.
Okay.
Into P to the power R.
P to the power R. Okay. So can you tell me how did you get this expression?
That has told.
Sorry?
That has told in the lecture, ma'am.
So, but do you know how do you get this expression?
Yes, ma'am. I can do that.
Okay. Shrochan, do you want to explain this?
Yes, ma'am. K minus 1 C. Yeah.
Yeah, please go on. Yeah, you can continue. Please keep yourself muted. Okay. So,
shall I tell them?
Yeah, please continue.
Yeah, sure. So basically what they want is to have R success in K trial. So it means that R minus 1 success can happen in any of those K minus 1 trials. It's nothing but a binomial distribution.
Yes.
So nothing but
nothing but a binomial distribution.
Yeah.
Right?
K minus 1, C R minus 1.
Yeah, okay.
1 minus...
You can mute. There is a lot of noise coming in. I got that. Okay. That was right.
Yeah, sure.
Okay. Yeah. So what is happening here is like on the first, if the Rth success is happening on the kth trial, then it means on the first k minus 1 trial, you should have R minus 1 successes, right? So this on the first k minus 1 trial, it is nothing but a binomial distribution, kind of binomial distribution, where your number of trials is equal to k minus 1 and you are interested in R minus 1 successes, right? So n choose k, so k minus 1 choose R minus 1, p to the power R. So what is p to the power? So k minus 1, n choose k is k minus 1, choose R minus 1, p to the power R minus 1, because it is R minus 1 successes, and 1 minus p to the power k minus 1 minus R minus 1. So it will become k minus R. And on the kth trial, you have the success, right? So this is just going to be into P. So if you solve this, you will get just K minus 1 choose R minus 1, P to the power R, 1 minus P to the power K minus R. So this is how you get this expression.
Excuse me, ma'am.
Yeah.
How you get this P here, last P?
Because on the kth trial, you have the Rth success. Because on the kth trial, you have the success, right? So that P you will have to multiply.
It's like
some probability of success is P.
Yeah,
right?
Probability of success is P. It is again the same repeated Bernoulli P trial.
Okay.
And can you explain that? Okay.
Yeah.
And for R minus 1 successes, the same probability is P. I mean, like.
Yeah, because it is again the Bernoulli trial. Each of the trials are Bernoulli. It is just what it here it's representing that on the kth trial you should have the Rth success. So in case of geometric distribution, you had on the kth trial you should have the first success, right? But here I am saying that on the kth trial you should have the Rth success. It means the first K minus 1 trial you should have R minus 1th successes, right?
Okay.
So each of the trials are Bernoulli P trial, and all are independent. So the first K minus 1 trial, you should have R minus 1 successes. So basically this first K minus 1 trial, it is nothing but a binomial distribution. Okay? So how do you write the distribution of a binomial? It is n choose k. So n in this case K minus 1. So K minus 1 choose R minus 1 because R minus 1 successes should be there.
And
so
K minus 1 trials.
P to the power number of successes, that is R minus 1 in this case. 1 minus P to the power n minus K. So n is K minus 1. K is R minus 1. So K minus R. And the last trial was success. So I'm just multiplying by P. So this is the probability distribution of negative binomial.
I see.
Ma'am, can you explain this K minus R part? I'm getting confused.
Yeah, so 1 minus, so if you have, let's say you have a binomial distribution, you have a binomial distribution with n equal K minus 1 and P equals, P is something, okay? And your K is, sorry, number of successes is R minus 1. So if you have to write the probability distribution of this, where n is K minus 1, what will you write? You will write n choose K. So n is what in this case? It is K minus 1. Choose R minus 1. So n choose K. P to the power K. So what is K in binomial? It is number of successes. In this case, number of successes is R minus 1. So P to the power R minus 1 into 1 minus P to the power n minus K. So n was total number of trials. So in this, it is K minus 1 minus number of successes. So number of successes is R minus 1.
R minus
minus R plus 1 into P.
Okay, okay, I got it. Okay, thank you, ma'am.
So, ma'am, the PDF of negative binomial random variable
not
is
PDF,
this
PMF.
one. Sorry,
Yeah.
PMF.
This, yeah, this one.
Yes, ma'am. I was wrong. I left into P at the last.
P, sorry, can you repeat?
Ma'am, the formula that I told you.
No,
I
the
left,
formula you told me was right. So here it was P to the power I minus 1 into P. This is same as P to the power R. So this was right, but you didn't know like how it came.
Yes, ma'am. But I forgot. Sorry, I left that into P at the last.
Yeah, right.
No, that the P power R minus 1 into P is PR. No?
P to the power R.
Okay. Yes, ma'am.
Yeah.
So one are the same.
Okay.
Both are the same. Yeah. So,
ma'am, where P is the probability of success in Rth trial.
P is the probability of success, not on the Rth trial or something. Each of the trial are Bernoulli. Each of the trials are Bernoulli P. Each of the trials are Bernoulli P, where P is probability of success. not the probability of success on Rth trial.
Okay, ma'am. Got it. Thank you.
And then it seems similar to binomial distribution. Then why a new name? It seems similar to binomial distribution, right?
It seems similar to binomial distribution. Yeah, but in the binomial distribution, we were interested in number of successes in total n trials, right? But in this case, we want on the kth trial, you should have the added success.
Okay, a particular success on a particular trial we are talking, right?
Particular success on a particular trial we are talking about.
So that's the differentiating point.
Yeah.
Okay.
In that case, now can we correlate this with geometric distribution?
So yes, so if from here you can go to the geometric distribution. So if k equals, if you put r equal 1, then it becomes a geometric distribution.
Yeah, sir told to keep r as 1, so it will be negative to geometric.
You put r equal 1, it will become geometric distribution.
From negative to geometric.
Could you explain this one, please?
Okay, so negative was getting Rth success on the k trial. Yeah. So if this is a k trial, you're getting your Rth success. So and geometric is on the kth trial. Kth trial, you should have first success. So if you just put k equals 1 here, it becomes geometric, right? So this was your formula. This
so
was your formula.
All our failures before that.
Yeah, you just put r equal 1 here. So you'll get what? You will get k minus 1, choose 0. P to the power 0. 1 minus p to the power k minus 1 into p. Right? So k minus 1 choose 0 is what? It is just 0. 1. And it is 1. K minus 1 choose 0 is 1. And it is 1 minus p to the power k minus 1 into p, which is same as a geometric distribution. Right?
Okay, ma'am. Please move forward, ma'am.
Sorry. Yeah. So we can also look at one or two problem on geometric and negative binomial.
Yes, ma'am.
Yeah. So I will take the example from the activity questions.
Are we discussing Poisson random distribution?
Yes, after this, it is Poisson distribution.
Okay.
Okay, so before that, there is one more concept that was there in geometric. So this expression is good to remember. What is the probability of getting the first success within the first k trial? Okay, so you have the k trial, and what is the probability of getting the first success within the first k trial? So either you can get the first success on the first trial, you can get the first success in the second trial, or you can get the first success on the kth trial. So you will have to add all these probabilities, right? So probability, if you have to find probability that x is less than equal to k, so this is going to be probability x equal 1 plus probability x equal to 2 plus up to probability x equal k. So what is probability x equal 1? What do you mean by probability x equal 1?
First trial.
First success. On the first
Yes,
trial,
on the first trial.
right? So it is just P. So what is probability X equal to?
That means first trial is failed and the second
One
trial is
Okay, so first trial is failure and second trial is success, right?
success.
So first trial is failure means probability is 1 minus P and second is success is P. What is the probability that probability X equal 3?
1 minus P whole
1 minus P to the power square
into P.
1
into
into P. And if it has to go to K, it is 1 minus P to the power K minus 1 into P. Right? If we want to solve this expression, I can take P common, right? If I take P common, it is just 1 plus 1 minus P plus 1 minus P square up to 1 minus P to the power K minus 1.
Yeah.
Okay. Now you see that this is a geometric series, right? What is geometric series? In geometric series, all of the terms like ratio of the first and second term, second and third term is constant throughout. So if you look at the common ratio here, can you mute yourself? It's a lot of noise. Okay. So R equals 1 minus P, right? So this is a geometric series. And what is the sum of the geometric series?
A by 1 minus R.
If R is less than 1.
A upon 1 minus R. Anybody else?
Ma'am, A into 1 minus R ka power n divided by 1 minus R.
Okay, what is n here?
Number of terms.
Number of terms. What is R here?
Common
Ma'am, common difference.
And
Ratio.
A is the first term, right?
ratio.
So here we know that total number of terms is how many? How many terms are here?
N times.
N K minus 1.
N terms.
K minus 1 terms. Here we have K minus 1 term.
Okay. K minus 1.
Okay.
Sorry, K terms. Sorry, K terms. You have K terms here. First term, second term, third. Sorry, your voice is not clear. You have K term, right?
Yes, yes.
So,
Yes,
and what is A? A is just 1.
No, 1.
Yeah, A just 1. So A into 1 minus. So 1 times 1 minus R to the power n. R is 1 minus 1. R 1 minus P. So 1 minus P to the power K divided by 1 minus R. So 1 minus P. So if you solve this, you will get 1 minus P to the power K. So this probability is probability of getting the first success within the first K trial. Right? Is this clear? This expression is clear?
Which distribution is this now?
Yes, ma'am.
Can you repeat the last part, madam, where you just said you substituted these values? Okay, fine.
Wait, yeah.
Now it is A into 1 minus R power n. Okay. So this is the sum of all terms, means sum of all the probabilities, or how is this?
See, so we had what we were interested in finding what is the probability of getting the first success within the first K trial. Okay, so within the first K trial means either you can have the first success in the first trial or in the second trial or on the K trial. So we'll have to add all this probability, right? So probability X equal 1 plus probability X equal 2 plus up to probability X equal K.
Okay, that is clear.
So if you solve this, this was clear, right? This is P plus 1 minus
P plus P into 1 minus P, P into
all this is clear.
Yeah,
so
that is all.
If you add this, you take P as a common and you will have 1 plus 1 minus P plus up to 1 minus P to the power K.
Okay,
right?
This is also clear.
Now,
GP is also clear. Yeah.
Now this is a geometric series.
Correct.
What is the sum of a geometric series? It is given by A times 1 minus R to the power, sorry? Oh, sorry, yes, K minus 1. Yes, K minus 1. Thanks. So A times 1 minus R to the power n upon 1 minus R. Fine. So
Okay.
A in this case is 1. A is the first term.
Correct.
So A is 1. What is R here? A is 1. R is, can you tell me what
R is
R
1 minus
is?
P.
1 minus P. And what is N? N here?
K minus 1.
Not K minus 1, it is K.
Sorry, N is K terms. Yeah, okay.
K terms. So you just substitute. So this is the sum of the geometric series, right? You just substitute everything in this formula and you will get your final value. So you will get 1 minus P to the power K.
So will this automatically equate to 1, madam? That was what I was trying to understand.
Sorry?
Will this summation lead to 1 or will it be any?
It is not 1, right? So you put A to be 1 and 1 minus R to the power N. So R is what? 1 minus P to the power N and N is K.
Allow me to rephrase. What does this represent actually in our terms of experiment? What does the sum of all the terms represent for us?
Yeah, so sum of all the terms, you mean this term, right?
No, I mean like we have A into 1 minus R power N by 1 minus R, and that is all the probabilities that we're adding up.
Yeah.
Now what is that I have? How do I interpret this information that I have with me? Summation of all the terms.
You mean this term?
Yeah, I got an expression also at the bottom of it, right?
This is the probability.
This
is the probability of getting first success within N trial.
Within the first K trial, yeah.
Within K trial, within first K trial.
Okay, no probability of success within the first K trials. Okay.
Yeah, probability of, yeah.
Is it a special case of geometric distribution or what?
No, it is not anything a special case. It's just a derivation. Like if you have to find like what is the probability that you get the first success within the kth trial, then you have a simple formula that you can just write.
Madam, earlier we had also given an expression which is P into 1 minus P power K minus 1.
P into 1 minus P to the power K minus 1. Yes, that is geometric distribution.
And this is the probability. This gives me the
so that probability was like what is the probability that you get the first success on the kth trial, this one.
Correct.
So this represented what is the probability that you get the first success on the kth trial, and what does this represent is what is the probability that you get the first success within the first k trials. There is a difference, right?
What was the above first what you told?
So
about
this expression probability like P times 1 minus P to the power K minus 1. What does it represent? It gives you the probability that your first success is on the kth trial, right? It just on the kth trial you should have the first success, but this probability here, this probability is for like the first success within the first k trials. There's a difference within the first k trials. So if you are saying within the first k trial, it means either you can get the first success on the first trial or on the second trial or on the third trial up to on the kth trial. So you will have to add all those probabilities. But that's not the same as the previous case. It just said what is the probability that you get the first success on the kth trial.
And it is first success or that only success on kth trial?
First success on the kth trial. In geometric, we talk about the first success on the kth trial. Whenever you have sorry?
Because we will get only one success.
No, it's not like that. Like if the same thing that I had given the example to you before, like you have a coin and you're tossing it repeatedly and you are interested in finding like what is the probability, like on what trials you are going to get the first head, right?
And trial. Sorry, infinity.
Yeah. So first head can go can start from either 1 or 1, 2, 3 up to infinity. So if I fix that, let's say I'm getting my first head on the third trial, right? So what is the probability that you get the first head on the third trial? What is the probability? Suppose your coin is fair.
Can we interpret this as a cumulative distribution?
No, first answer my question. Like
Sorry,
what is the probability that you get the first head on the third trial?
The third trial.
Yeah, on the third trial.
1 by 8.
That would be the
Seven
first
by eight.
formula.
7 by 8.
7 by 8.
Yes.
Okay. Why is that?
So 1 minus probability of getting success is half. So 1 minus half is half, right? And to the power 3, so it comes down to 1 by 8. So 1 minus 1 by 8 is 7 by 8.
So it's
No.
12
But it is actually
Yeah.
it is k minus 1.
Ma'am,
So
I
it is,
got 1 by 8.
1 by 8.
Yes, ma'am.
Ma'am, what is
Yes,
the question, ma'am?
Ma'am, how, ma'am?
On the third trial, you are
By
saying?
8.
or-
Just put on the formula.
I will
lemma of
write.
geometry.
Okay,
Just a
wait.
second.
I will write the question
Please
here.
write,
I will
ma'am.
write the question here. So you toss a coin repeatedly. I will write something else. Okay. The question is toss a coin repeatedly. The coin is fair. Okay. So what is the probability that you will get first head on the third trial?
This will be 1 by 8, ma'am.
It will be 1 by 8.
Ma'am, this will be 1 by 8. Ma'am, can you write down one more question, ma'am?
Ma'am,
The
how, ma'am?
derivation.
Please first explain this.
Okay, so how is it 1 by 8?
Yeah,
Okay.
ma'am.
So what is the probability that you will get first head on the third trial? So if I say this model, okay, so do you agree that this model is a geometric distribution?
Yes.
Right?
Yeah.
Because we are interested
Because
in the first
infinity.
success on first
Infinity
success.
trial.
No,
On
it's
third
not
trial.
about
On third trial.
infinity.
First success
We are
on third trial.
we are
First success
interested on the
on-
first success, right?
On third
On the
trial.
third trial.
Yeah, we are interested on the first success. So whenever it happens, it is basically a geometric distribution. So even if I don't use the geometric distribution, you just have 3 trials, right? So if my first head should come on the third trial, it means on the first 2 trials, it should have tail, right?
Tail.
Yes,
So tail
ma'am.
and tail. So what is the probability of occurrence of tail? It is
1 by
1 by
2.
2.
1 by 2.
It is 1 by 2 and it is 1 by 2. It is just 1 upon 2 to the power 3,
2 power 3.
right?
1 by 8.
Now, if I say this is a geometric distribution, so each of the trial is Bernoulli P. So what is P here? It is 1 by 2.
1 by 2.
1 by 2.
Each of the trial is a Bernoulli 1 by 2 distribution. Bernoulli 1 by 2 distribution. Now, if you have to find probability that x equal 3, where x is geometric distribution with p equal 1 by 2, then probability x equal to 3 is going to be 1 minus p to the power k minus 1, that is 2 into p. So p is basically 1 by 2. So this is going to be 1 upon 8, right?
Yes, ma'am.
Mhm.
Ma'am?
So in case of Bernoulli and geometric, both cases the trial is, probability is same.
It's not about Bernoulli or geometric. I mean, we are saying that each of the trial are Bernoulli, right?
Okay.
Each of the trial is Bernoulli. So I have a coin, I have tossed it once. So I can have a head or I can have a tail. If I am defining my success to be head, so success is head, failure is tail.
Tail.
Now again, I am tossing the same coin and the tosses are independent. Again, probability of, again, the success is head, failure is tail, and probability of success, probability of failure is same. Now here, the question that has been asked is, what is the probability that you will get first head on the third trial? It means the first success. You're talking about the first success here, right? So whenever the first success comes, it basically represents your geometric distribution.
Okay.
So it is nothing but a repeated Bernoulli trial, correct?
Okay. Ma'am, just a couple of minutes back we did a derivation to find out the first success within certain number of trials, right? So if we modify this question and ask that what is the probability of getting first success within third trial? Within third trial, of course, third trial included.
Let's try this. So what is the probability that you will get first hit within I will just
7
write
by
here.
8. 7 by 8, ma'am.
Within the
third trial, of course, third trial
Third trial.
included. Of course,
Yes,
third
ma'am.
one is included.
Yeah, third trial is included.
It's 7 by 8.
Yes, here it will come 7 by 8. 1 minus.
Okay,
One
take
minus.
the answer.
7 by 8.
7 by 8.
7 by 8.
Yes, ma'am.
Ma'am, how
We
many?
use the
Any other
second
answer?
formula.
Any other answer?
I think it's a 1 by 8.
1 by 8, okay. Okay, so these two are the answers that we got. So now the question is, what is the probability that you will get the first hit within the third trial? So it means you can have the first hit on the first trial, or you can have the first hit on the second trial, or you can have the first hit on the third trial.
Third trial.
Right? So you will have to add all these probabilities. So what is the probability of this probability that the first hit
1 by
occur on
2.
the first
1
trial?
by 2.
It is 1 by 2. Right? What is the probability that you get the first hit on second trial?
1 by 2 into 1 by 2.
4.
And this is 1 by 8.
1 by 8.
Right? So if you add 1 by 2 plus 1 by 4 plus 1 by 8, you are going to get, this is 2 upon 8 and 4 upon 8. So it is 7 by 8.
Ma'am, can we also think like this? Like, not getting ahead in any of the tosses? 1 minus not getting ahead in any of the tosses?
Yes.
1 minus not getting head in any of the tosses.
Yes.
Yes.
That was 1 minus 1 by 8.
1 minus p raised to something, and probability of success is p. So,
Madam, I have one
ahead,
question
ma'am.
on the earlier expression you showed on the summation.
Okay.
It is on the numerator when we say 1 minus r power n is equal to k, or is it k minus 1?
N was k.
N is k,
Because we had 1 plus 1 minus p plus 1 minus p square plus up to 1 minus p to the power k minus 1.
Correct.
So total you have k terms here. K terms, right?
Okay. Got it. Sorry.
Okay. So we'll move to the Poisson distribution.
And how do you represent negative binomial distribution? Like a Bernoulli, you said Bernoulli P, binomial NP, geometric P. Negative binomial distribution is also NP or NP? There's also a R. That's the reason why I'm asking.
R.
There is R
NPR.
also.
Yeah.
There is R also, NPR. So
R is a success. I mean, it's like that.
Sorry.
What does R represent there? It is the success.
R is R is success on a particular trial.
On particular trial. Okay.
Okay, so the next is Poisson distribution. So this is also a discrete distribution and
hypergeometry.
Okay, hypergeometric is also there, but I assume that also you have studied in your stats one.
No.
And this is more important.
Poisson is more important.
Hypergeometric you have studied in stats one course, right?
Right, ma'am.
Yeah, so that part you please go and check on your own. It is not much.
Ma'am, we will get this PDF.
You get this PDF. Okay, this is not fair, but yeah, we'll provide you some PDF for week 0.
Yeah, ma'am, sure.
Ma'am, you can
Please.
provide this. We don't need fair. It's well defined here.
Okay, I will try to clear a few things and can give it to you.
Ma'am, please don't clear anything.
Yeah, ma'am, just keep it as it is.
Okay, fine.
We also love your handwriting, ma'am.
Okay, it is not so good. All right. So in case of Poisson distribution, what happens is like basically all the events that occur like in a particular time interval, they should be independent, and the rate of occurrence of the event that we denote by the parameter lambda, that should also be constant. Like if we say, for example, number of accidents that happens on a highway on each week. So such kind of situation models your Poisson distribution where lambda will be fixed. I mean the rate of occurrence of the event. So event in that case is number of accidents, right? So that is going to be fixed, and in each week, like each week number of accident that happens on a highway is going to be independent and they are random, right? So such kind of situation when it happens, I say it models the Poisson distribution. So many such examples that you can take is like number of telephone calls that you receive at a call center in a 1 hour interval. So in each 1 hour interval, how many telephone calls you receive at a call center? Okay, so such this models about Poisson distribution. Okay, number of car accident that happens on a highway per day or per week. So such situation models Poisson. Number of radioactive particles emitted in a minute. Number of orders placed per minute on a website. So in each of the case, your parameter lambda is going to be constant. That is given, that is nothing but rate of occurrence of the event. So lambda should be constant, the first thing.
How to differentiate between a binomial and this one Poisson distribution, ma'am?
How to differentiate? Yeah, so in Poisson
In Poisson, we don't have n.
Sorry, Poisson and binomial you said, right?
Yeah.
Yes, ma'am.
Yes, ma'am.
Poisson and binomial.
Yes.
Poisson and binomial.
Yeah, so in binomial, you know the number of trials. There you have Bernoulli trials, right? There you have Bernoulli trials, but here it is not like any Bernoulli trial or something. Here you have some fixed time interval, like let's say each second or each minute, each hour, each day, every week, every month. You have such time interval or some particular space, and there you're talking about the occurrence of an event. Okay, like in first, let's say in the first 1 hour an event occurred, in the second 1 hour an event occurred, in the third 1 hour an event, the same event occurred, and all these events are independent of each other. So if I'm saying this is first time interval, second time interval, third time interval, so in each of these time interval an event has occurred, and all these events are random one and independent of each other. So such kind of situation, like as I said, number of accidents per week on an highway. So each week there is some particular number of accidents that has happened, and they all are independent of each other. So whenever a situation like this happens, like we say it models the Poisson distribution, and the rate of occurrence of event is assumed to be constant. So lambda should be same for all the event. So in this case, what should be your range be? Like, okay, this is your range. So if X denote, so if you have a Poisson distribution, let's say X is a Poisson distribution.
Ma'am, I got a small doubt over here.
Yeah.
Let us say if I take the case of a particular company share price kind of thing, share market on particular day kind of thing, it could be a Poisson distribution, but I will not be knowing the number of transactions. That is, then I can't fix out that lambda, ma'am. Even though
so it is lambda is like the rate of occurrence of an event. How you should have some data, right? Like on the first
weighted average.
First star, you should have, it is kind of average.
Weighted average.
Yeah, weighted average, right?
Thanks, ma'am.
Ma'am, when we say rate is constant, what does it mean? Like number of accidents per week remains same or what?
Number of accident. Sorry, can you repeat?
When we say lambda is rate, right? And rate remains constant. So what does it mean? Like number of accidents per week remain fixed or what? Or number of telephone calls?
The rate, the rate at which the event is happening, we assume it to be constant.
So what does rate define here? Like let us take
the
an example.
Average. It's nothing but the average.
Yeah.
Okay.
It's nothing but the average.
Why are they considering it as a weighted average? When I mean average, I understood, but why weighted?
So it is like in a particular time interval, how many times, the average number of times that event has occurred. So okay, you haven't looked at the lectures, right, yet? Wait. So there was one or two example on a real life, like number of meteorites entering the Earth atmosphere. From there, how do you calculate lambda?
Yes, ma'am.
All that is explained there.
Number of people entering into the shop.
Sorry?
Number of customers enter into the shop.
Number of customers entering to a shop on a particular day. Yeah, such kind of situations like will model Poisson distribution. So how do you find lambda? If you're interested in that, you can just go through one lecture of this week 0 part 3.
Okay.
Where the Poisson distribution discussed, and you will see like how this lambda has been calculated. Okay. So this part you can check there. So if you have a Poisson distribution, we write this random variable as Poisson lambda, where lambda is a parameter. So the Poisson random variable has just one parameter, that is lambda, and it gives the rate of occurrence of the event. And it basically represents number of number of events basically. Okay, so wait.
Is there a relation 1 by lambda is equal to mean?
Yes, lambda is nothing but mean. So if you have to find the expectation of the Poisson random variable, it is nothing but lambda. Even the variance of this random variable is lambda. So I think all this you will see in expectation and variance in week 3.
Lambda is right? You are telling that the expectation and variance are also equal to mean?
Expectation in case of Poisson distribution, the expectation and variance both are equal to lambda.
And the mean is also the same, is it?
Yeah.
Lambda equals to NP.
Lambda equals
no, lambda is to NP, right?
NP.
NP.
Yes.
NP.
So when n is very large and p is very small, so
the 1 by lambda, is there any relationship?
1 by lambda. So if you go to exponential distribution,
e raised to
minus lambda.
E raised to minus lambda.
That is 1 by
lambda.
e to power lambda.
No. In a problem statement.
Sorry, yeah.
In a problem statement, is an 1 by lambda is given, then our mean is given. We can really start progressing the problem with the mean data as lambda.
If the problem statement mean is given, that is lambda.
That's lambda.
Yeah.
Thank you, ma'am.
So the distribution function in case of Poisson distribution is given by e to the power minus lambda to the power k by k factorial, where k varies from 0, 1, 2 up to infinity.
And if the problem statement has n and p, then np is lambda.
Yes, yes.
Okay. Thank you.
So,
ma'am, how relevant is the Poisson distribution with the real life? I mean, for example, in the shop, if you are taking a rate like the number of shops, number of customers entering into a shop is like, for example, 30. But there are some prime times, like the there will be a rush time. There will be like in the morning, the expected number of customers will be so much less. So if you're taking it like, if you're generalizing it, how accurate is that? And is there any other parameters to rectify those errors or something like that?
Yeah, that is why we have assumed our lambda to be constant. I mean, for each time interval, I'm assuming that my lambda is constant. Because if we are talking about every day, so on an average, every day you are getting the, let's say, same number of customer.
We will took the average number of customer arrive at each day.
Sorry?
We will took the average number of customer arrive each day, right, ma'am?
Yeah, right. So lambda is like average number of customers that you will get each day.
Sir, you can check even the standard deviation concept also. Sir. Then you can get the correct understanding of what ma'am is telling.
Actually, can you repeat a little bit, because I got a call in between that. I'm extremely sorry for that. Is it okay?
Yeah. Okay. Yeah. So what I was saying is, so lambda we assume to be constant, and lambda is like average number of rate of occurrence of an event. So if you're talking about number of customers that are entering in a shop each day, so yeah, at some point of time it will be more crowd, and at some point it will be less crowded. So we are talking about each day. So on an average, number of customers that come each day is almost constant, right?
Okay,
so
yeah.
That is why lambda we are saying it is a constant.
Ma'am, there was an example, firewall
Yeah.
example.
Sorry.
Firewalls example. Sir has to.
Yeah, number of fireballs entering the atmosphere.
Yes, ma'am.
Yeah.
Ma'am, can you help me that I don't know how that finded the lambda.
Okay.
Actually I didn't understand that that part of that example.
Just wait. Let
Sir,
me see.
yeah, sir has told that average rate is equal to
was
total number of fireball divided by 276.
Meteorite, right?
26 is number of incidents. That is the
So, okay. Let me share the screen.
Ma'am, are you explaining negative binomial, ma'am?
Negative binomial, I have already explained.
Okay.
So there we were saying like in 276 months, number of fireballs entering the atmosphere. So 24 times number of fireballs that entered is 0. number of fireballs that entered. So on one fireball entered 54 number of times. So you have some information like how many number of times, how many fireballs are there, and how many times they have entered the Earth atmosphere.
Are you writing something on the screen, madam? Because I'm not seeing.
What is the question, ma'am? What we are discussing now?
You had asked about fireball and
yes, ma'am. Fireball question.
Yes.
Sir has explained on the Poisson distribution lecture.
Yes, right. So there you had like 0 24 times, 154 times, 276 times, 352 times, 437 times, 521 times, 6 7 times, 7 3 times, 8 fireball 1 time, 9 0, and 10 1. So the question was like in 276 months. So you have total of 276 months. And in these 276 months, like in 26 months, you have 0 fireball that entered the Earth atmosphere. 54 months, you have 1 fireball that entered the Earth atmosphere. 76 months, you have 2 fireball into the Earth atmosphere, and so on. Right? So what is the basically arrival rate? We have to find the lambda, right? So
yes,
rate of occurrence of an event. So what is the rate? So how many, how will you find the rate? So total number of fireballs that entered.
Yes, ma'am.
Right. So how many fireballs have entered?
Ma'am, 55. Sum of all the above row is 55.
Okay. And so total number of fireballs that have entered, and out of
it is, ma'am, total number of fireball entered.
276.
No, it's a month. Okay, yes, ma'am. Yes.
So what will it get here? 5 divided by 276.
0.19.
0.19.
Sir has told something 2.5217.
Okay. Okay, just let me, I will check this one. Okay.
Ma'am,
it's a 0.199.
No,
something must be wrong here. I will check this and
same thing was with my same thing was with above example also, radioactive decay.
Which example?
The example before this radioactive decay example. Not, ma'am, in your lecture, the sir has given this example.
Radioactive decay, right?
Yes. There was same problem there. Please have a look on that example also.
Yeah, okay, I will check.
Thank you, ma'am.
Yeah.
Did sir explain 2.47 or something?
Sorry?
I mean, did sir explain 2.47?
I'm not getting what you're saying. Can you repeat?
No, I mean, did sir explain 2.47?
2.47.
I think so. If I don't know, I just did a rough calculation, and then if that's so, then it is your.
Sir has told 2.52.
2.52. If it is 2.47, then 276 months is like 13 years, and then if we are dividing by 13 years, we'll be getting 2.47. If that's so, it will be your.
No, the answer is something else. Wait.
Okay.
Okay. So do you want to see some problems on Poisson distribution?
No, ma'am. No, ma'am. Please move
Ma'am,
forward because we had wasted a lot of time.
Sorry.
Okay.
Madam, if you can solve one problem, it will be helpful, I guess. Just one.
Yeah, just one. Yeah, one is fine. So first, you also can take some time and okay, I will just share the screen. Okay, you can try out the first problem from here. Just try it for a minute and maybe you take some 5 minutes, and then if you have any issue, like I will help you out.
Is this from the weekly tutorial or where is this from, madam?
Sorry?
I'm trying to figure out where this is. Activity question 5.
First problem. You can see the screen, right?
Yes.
Try to solve the first problem.
And 2 divided by e to the power 2.
2 divided by e to the power 2. Okay. I will keep. Okay. Let others also solve. I will just keep this.
Ma'am, it's 0.27.
Uh, 0.27. Okay. Anybody else? 0.271. Okay. So all of you are able to solve this problem. So all three answers that I've received are all correct. So all of you are able to solve?
No, madam. Can you please explain that? I'm really sorry, but I don't know how to solve this one. That's the reason I just kept going.
Yes,
ma'am. Okay. Can you just take 1 more minute and try to think about it? Just try to find what is your lambda here. What exactly you have to find. Okay. The question says, on an average, 240 ambulances arrive at a hospital per hour. Assuming that the number of ambulances arriving at a hospital follows the Poisson distribution, find the probability that one ambulance will arrive in a 30-second time interval. Okay. So, what is it that you have to find there? What exactly do you have to find here?
Lambda.
Ma'am,
Yeah, tell.
The probability that one ambulance arrive in 30 seconds of interval.
30-second time interval, right? Yeah. So now you have to take okay. So can you tell me how will you find your lambda here?
Ma'am, we have to convert. Here lambda is given in hours, 240 hours, 244 ambulance per hour. It's and it seems like mean. So we can convert this on seconds. Sorry, how many ambulance arrive in 30 seconds?
Okay. Yeah. So in 1 hour, if 240 ambulances arrive, it means in 30-second time interval, around 240 upon 3600 into 30 ambulances will arrive. So that is nothing but equal to 2. So if you take each 30-second time interval, on an average, 2 ambulance will arrive. Okay. So that is your lambda. And you have to find probability x equal to 1. So you just have to use the formula, that is e to the power minus lambda, lambda to the power x upon x factorial. We know the lambda, we know the x. You just have to calculate it. So it was given that in 1 hour time interval, you have 240 ambulances arriving at the hospital. So if you have to find for 30-second time interval, so in a 30-second time interval, number of ambulances that will arrive is 240 upon 3600 into 30 ambulances, and that is nothing but 2 ambulances. Okay. So in each 30-second time interval, on an average, 2 ambulances are arriving. So this is your lambda. Lambda equals 2. Now, what is the probability that number of ambulance that arrive in 30-second time interval is equal to 1? So this is given by e to the power minus lambda. So lambda is 2. Lambda to the power x. So x is 1 here upon x factorial. So this is nothing but 2 times e to the power minus 2. And it will come out to be 0.271.
And so we have to find out lambda with respect to the time interval given in the question, right? Because 240 itself is a lambda. We talked about with respect to
R. So if you had to, you could have also done like you could have converted
30 seconds into R.
Yeah, 30 second into R.
Okay. So lambda should match with the time interval in the question, right?
Yeah. So basically, we wanted like in each of the time interval, your lambda is constant, right? So we had to find for 30 seconds. So that is why we found the lambda here.
Correct.
This lambda here.
मैम अगर हेलो
Yeah.
मैम अगर ये जैसे बोला ना कि 30 सेकंड में एक एम्बुलेंस आया इसकी प्रोबेबिलिटी निकालने के लिए,
हाँ,
तो अगर इसकी जगह कहते हैं कि मतलब 30 सेकंड की जगह 120 सेकंड या फिर कुछ अदर टाइम देते तो हम के वैल्यू कितना देते?
तो अगर 30 सेकंड की जगह 120 सेकंड होता तो 240 upon 3600 into 120.
नहीं ये तो इतने ही रहते हैं, मतलब कि 30 सेकंड ही। और इसका ये जो बाद में बोला गया ना कि एक एम्बुलेंस आया 30 सेकंड में, उसके लिए तो मतलब कि एक 30 सेकंड की जगह उस टाइम इंटरवल को बढ़ा के सेकंड वाले को अगर 120 कर देते या फिर कुछ और कर देते।
I'm not able to get your question.
So what is trying to say, the question we are asking now, that what is the probability of getting one ambulance in 30 seconds, right? So
Okay,
in that
yeah.
line, if it is written that what probability of getting one ambulance in 120 seconds, he's saying that.
Yeah, exactly same thing. So यहाँ पे 30 सेकेंड है तो 120 सेकेंड के लिए कितने एम्बुलेंस आएंगे? So 240 upon 3600 into 120 जो कि होगा 38, right? 8 ambulances. So in place of 2 here, यहाँ पे 2 की जगह 8 हो जाता, right? So you just have to substitute.
के वही रहेगा, 1 ही रहेगा।
हाँ, के 1 ही रहेगा. So it will be 8 into e to the power minus 8.
Thank you.
Ma'am, are we done with theory of Poisson distribution?
Sorry.
Are we done with theory part of?
Yes, we are done.
I have some doubt on activity quotient.
Okay. Tell me which question.
Activity quotient 1.5.
Okay. Activity quotient 1.5. Yeah.
So my point is now I have to draw the table and then have to find this joint PM, joint probability, or can I draw it directly? Like.
So here you have like a fair coin is tossed 4 times. And let X denote the number of heads on the first toss, Y denote the number of heads on the 2 tosses, and Z denote the total number of heads in 4 tosses. So you have tossed the coin 4 times, and your X denote. So if you have to, let's say, find the first problem, so X, Y, Z equal 0, 1, 2. Yes. So X denote number of heads on the first toss. So first toss you should have 0 head. 0 head on the first toss. It means on the first toss you should have a tail.
Tail, yes.
Right. Then second is Y should be 1. So what is mean by Y equals 1? It is number of heads on the first 2 tosses. Right. So
that means first should be tail, second should be head.
Yeah, second should be head. Right. And Z is what? Total number of heads in 4 tosses. So if total number of heads is going to be 2 on the 4 tosses, so either you can have T, H, H, T, or you can have T, H, T, H, right?
So, ma'am, I was trying to do it through the marginal and your conditional probability. So one way, when you're going from X to Y, answer is matching, but when you come to Y to Z to X, it's not matching. So could you help me out on this?
So wait. So you are saying, how are you trying to find out if X, Y,
so
Z?
X is equal to 0. X, I'm finding that the range X is 0 and 1. So
which problem is this?
This is from AQ 1.5.
Yes.
And we will discuss, you told that we will discuss joint conditional probability.
Joint conditional probability, right? Yeah, so let's do this first. So yeah,
X 0 1. If you over the range,
X was defined as number of heads on the first toss.
First toss.
Okay.
And Y is equal to number of Y equal to range is 0 1 2.
Y was defined as the number of heads on the first two tosses.
First two tosses.
Okay.
So 0 1 2 is a range.
Okay.
And Z is number of heads on the four tosses.
Okay, so 0
so
1
0
2
1
3
2 3
4.
4.
Yeah. Right.
So if you want to find the your joint probability, XYZ 1 2 3.
XY if XYZ 1 2 3. Okay.
Yes. So I'm taking Z FZ3.
You're taking FZ3.
If Y conditional Z3 into
Y conditional Z3.
2.
Yeah.
Into
okay.
If X condition Y equal to 2, Z equal to 3.
Sorry, repeat, please.
Y equal to 2, Z equal to 3.
This is 1.
This is 1.
Okay, but how will you know the distribution of X given YZ?
So that's why I'm seeing that. I see, suppose FZ, FZ3. So I can see if I the probability of getting 3 heads in a 4 trial is 4C3 into 1 by 2 to the power 4.
Probability of getting?
Probability of getting 3.
3 heads on the 4
3
trials.
heads in 4 trials.
Yeah.
Is 4C3
e to the power 3.
1 by 8. 1 by 16.
Yeah.
So it's becoming 1 by 4.
Okay, yeah, 1 by 4.
Okay. Then on the second part, Z equal to 3 and Y equal to condition Z equal to 3, Y equal Y2. So I'm getting only 2 probability is 1.5.
So you should have like 3 heads, given that it is 3 head on the first 3 head on the first 4 trials. What is the probability that on the first 2 tosses it should be 2 heads?
2 heads.
Right.
Or maybe 1 head.
No, if you're taking this, it is 2 heads.
2 heads. Yes. So it's a 1.
So it can be T or H, or it can be H, HT.
Yes, yes.
Right.
So it's a 1, right?
Which one is 1?
If Y Z equal to 3, if Y condition Z equal to 3, 2. That second, but that you squared the.
Okay, yeah.
Yes, which is become 1, right?
This is coming 1, you're saying.
Yes, this is become 1.
How? Why it will 1?
Okay, no, sorry, it's become 1.5, right, ma'am?
This becomes 1 by half, right?
Yes, yes. And last part I'm just missing out, ma'am, sir.
So why is it like on the first trial it should be 1 head?
It should be 1.5, ma'am, also.
on the first trial, it should be 1 head. Again, it is 1 by half.
Yes, 1 by 16.
So it will come out to 1 by 16.
Yes.
Yeah, it is coming out. It will come out to 1 by 16. So this is basically what.
Answer is correct. Okay, I'm missing something.
Okay. Nice. Yeah. So somebody wanted to know about conditional, rational, and joint.
My point is now I have to, whenever I get this kind of problem, so I have to go through this. I have to make table, or I have to assume that the connection between this provided that.
Sometimes table is easier. Sometimes just looking at the events here and identifying the probability is easier. Like in this case, finding this was very easy, right? 1, 0, 1, 2. Like, you know what your X is, you know what your Y is, you know what your Z is, and you have tossed it 4 times. You can easily write down the events and find the probabilities. So you can also draw the table if you like if you find that to be more easier. So it depends on like your choice.
I have a question on the way the problem was solved a little earlier. You were showing something. You started with fz of 3 and then fy conditional z on 3 and that being 2.
Yeah.
And then
So
why did we go in the opposite direction?
Yeah. So if you have say xyz of xyz, so this joint probability, you can write it as conditional times marginal. So I can condition it on x, let's say x given yz.
X equal 1.
Okay. X. Let's take it as xyz. So if it is probability x given yz, so this is xyz divided by probability of.
It should be
so fyz, right? So yz. And again, this yz, we can write it as f y given z of yz. Basically, you should write z equal to z of y into probability of fz of z. You can also write it as f of xy given z. You can write it in many ways, xyz into fz of z. Sorry, f probability x given yz and again yz. So you can write it in many ways you want. I think it's the same thing. Repeated the same thing. So f.
Okay, and for 0, 1, and 2, how are we solving it? Basically, you started off with saying we get f of z for 2.
So for 0, 1, 2, right?
Yeah.
So
f x y z of 0, 1, 2.
Fix.
So if you write it as f x given yz, so yz is taking 1, 2 of 0 into fy given z equal to of 1 into f x of 0, right? So sorry, fz of 2. So what do you mean by fz of 2? It means on the 4 tosses, you should have total of 2 heads, right?
2 heads, yeah.
So 4 tosses should have 2 heads. So it is going to be 4 choose 2 p to the power 2.
1 by 16.
This is going to be 1 by 16, right? Now if y given z equal to of 1, it means if on the first 4 trial, first 4 toss, you have 2 heads. You have 2 heads, but on the first 2 tosses, so y was number of heads on the first 2 tosses. So if number of heads on the first 2 tosses is just
it should
1.
be 6 by 16.
Sorry?
4c2 is a 6. 4c2 is 6 into 1 by 16. That one. FZ probability. FZ2.
4 choose 2 is 6, man. That's what it is.
4 choose
Okay.
6.
Yeah.
6 divided by 1 by 16.
Yeah, 6 divided by 16, right? Correct. Now, if y given z equal 2 of 1, it means if on the first 4 trial you have 2 heads, and it means on the first 2 tosses you have just 1 head. Okay, so you can have many choices here. So you can have HT. So on the first 2 tosses it should be just 1 head. So
Correct.
it can be also TH. On total should be just 2 head. So it can be TH, HT. Then you can have
TT also.
No, TT is not possible, right?
No, if it's a 2.
So it can be HT, HT, right? This is possible. So HTTH, HT, HT, right?
Yes.
And TH, HT, and TH, TH, right?
Yes.
So these 4 are there. So it will come out to be 4 upon 16. That is 1 by 4. Now, if x equals 0, it means on the first.
But when we are looking at the conditional probability, we normally go by y of 1 intersection y is under the condition z is equal to 2, and then the probability of the entire thing, right?
Yes, right.
So that's what I'm actually
It
trying
appears
to
that table method is sort of a structured flow, and it is.
Sorry?
Tabular method, it has a better structure.
Yeah, table method has a better structure. Like, you have tossed the coin 4 times and you can just look at all the possibilities and write your answer.
The joint PMF and the margin PMF, we can get it and find the answer there.
Yeah, it's kind of very complicated here. I think let's just leave it. We can like why do you want to complicate this? You can that on the first trial you should have a 0 head, right? On the first trial you should have 0 head, so first should be tail. On the y denote 1, it means on the first 2 trial you should have 2 successes. 1 head. So the second is going to be H for sure, because you just want 1 head on the first 2 trials. So if first is T, then other is going to be H. And Z represent total number of heads on the first 4 tosses. So it has to be 2. So TH is fixed. So either we can have TH HT or we can have TH TH, right? So this is 1 upon 16. This is 1 upon 16. If you add it, you will get 1 upon 8.
Yes, ma'am. It's a simpler one.
It is very easy. Yeah.
But in exam, ma'am, I think our brain doesn't work that fast. We have to.
Yeah, then you can also go through the table method. You can write all the thought. It will have 16 possibilities.
Let's move to the.
It's a point, so it's become easy. But if it's a dice and everything, it become more complicated.
Yeah, right. Okay. Somebody had asked the conditional Marshall and joint distribution. Can you tell me?
Yes, ma'am.
Yeah. What is the doubt?
The lecture. The example on the lecture that sir has told that I didn't understood that. Lecture 1.4, ma'am.
Lecture 1.4. Okay, what is the doubt here?
Ma'am, the examples. Can you just give a small brief about them? Sir has told, I think, 3 examples.
Wait. It is week 1.5, 1.4. Right? Okay, not able to open this. Can you tell me what example was that?
You can take the second example or the first one. Should I read the question now? Sir has used that Poisson distribution, binomial distribution with joint conditional probability.
Joint condition. So for that one, you can go back to the previous session, YouTube recording. So that part has been explained in that session. Can you just go and just have a look?
Actually, I had not completed this part, so I had not attended that session.
Okay, so that was discussed there.
Sure, ma'am. And one thing more, that equality or that the sir has told that you can find joint PMF from conditional PMF.
Joint PMF from conditional PMF. Okay.
Or that thing. Can you explain us for 1 second?
So okay, so joint can be written as conditional times marginal.
Yes.
This is clear, right? So this is what it is mean.
Okay.
So if you have the joint distribution of xy, so you can write fxy of x comma y as fx given by of x times fy of y. Or you can also write this as f of y given x equal x of y into fx of x. So this is what is mean by like you can write the joint using the conditional.
Ma'am.
Right?
Okay, ma'am.
Yeah. So let's stop this here.
Just one quick follow-up question, ma'am.
Yeah.
Ma'am, like we're discussing today's session that probability of getting first success in probability of getting first head as a success in first 3 tries, right? So we got an answer 7/8, right?
Yeah.
So this gives a hint. This gives a hint that as the number of trial increases, my probability of getting first success is also increasing, right?
As the number of trials
is increasing, probability of getting first success is also increasing, right?
No, it is not true, right?
No, like probability of getting first head within 3 trial is 7/8. If I calculate probability of getting first head within 4 trial, it will be more than 7/8, man. 1 minus p to the power a we do.
Okay, wait. So yeah, you had this, right? So you are saying if I take here 4th trial,
yes, it will further increase. My probability will further increase.
So you will have TT, TH, correct? And this will become okay. The question was first hit within the 4th.
The probability,
will increase.
Increase.
Probability will increase because it says you will
that's
get.
what I'm saying, probability will increase.
Probability will increase. Yeah.
Yeah, probability of getting first.
Because as the number of trials are increasing, you know that success will happen.
Yes. So
it is you have more chance.
That's a fair assumption, right?
Yeah, fair assumption.
But in real life, many times it does not happen. Say, for example, even if I'm trying and doing some experiment where there are only 2 outcomes, I may or may not get success, right?
Sorry, can you repeat?
The probability will decrease. How it will increase?
Probability increases, ma'am. You just do the calculation because as my number of trials are increasing, right? So probability of getting
in this case, the probability will increase.
Probability is increasing, right?
This is because as the number of trial is increasing, you are more confident that your
more
success
accurate.
will
yes. But in reality, many a times it does not happen. Say, for example, even I have tossed a coin, but I may not get head even after 5 trials also. Correct?
Yeah, right.
So does it mean that theory does not support reality? Because theoretically it is saying that my probability is more than 80% of getting a head.
It's just a probability, right? I mean, we cannot.
It's all about chances.
Yeah, we cannot.
But it's 80%, man. 80% makes something.
We have 20% of not having.
Yeah, right.
It's a theoretical argument, ma'am. But when the weather department says that there is a probability of 80% rain tomorrow, then it rains.
It's not necessary.
Like there is always.
You are doing theoretical argument here. Leave it, ma'am. Okay. You are doing theoretical argument. Just remember one point: in real life, we are going to apply all these concepts.
Yeah, right.
Ma'am, is it just because of the number of samples for the population? The more it increases, the more values we get, the more better we can predict, right? It is the way. It is that way.
Sorry, more.
The more samples we are having, the better prediction we can do. Is that way, right?
That is the different thing.
That way only, but many a times it does not happen in reality. So what is going wrong? It is just a chance or something else which we are missing in our experiment. That's my question.
It's a chance that something can happen.
I think we can give an analogy for this. I don't know, ma'am. You can correct me if I'm wrong. Suppose if I'm checking one review, Google review, for example, and there is 4 rating by 10 people, but that I will not appreciate. But if it is by 1,000 people, 4 rating, that will definitely have some count because number of cases are more, so it is more reliable.
Yeah, that is true. But here, I mean, it is not.
In general, as the number of trials increases, the probability will decrease.
No, it's not like that.
Ma'am, you are missing the question. Probability of getting first success. Probability of getting first success.
I get your point. I got your point. So you're saying
again,
like
ma'am, again, when we are going to have your session, because that we left that mature question.
So next session is going to be on Tuesday. So
that
is solve with a session. Maybe next Friday.
Okay, ma'am.
Yeah.
Okay, ma'am. Thank you, ma'am.
Yeah.
With your great session today. We explained so many concepts.
Yeah, thank you, ma'am.
Yeah, thank you all. Good night.
Thank you, ma'am.
Thank you very much, ma'am. Thank you. Bye.
Clarified many doubts.
Thank you, ma'am.
Yeah, thank you all.
Thank you, ma'am.
Yeah, thank you.